Hello! In this video, I am going to go through the in-class activity covering functions in my fall 2024. In this first question, got to click on the right screen. In this first question, we have the description arguments for a function being described. I then tell you the calculation, and then I tell you what it should return. This is an example of how it should be used. So looking at this, I can see that, all right, well, this is how it's used. That means I'm passing it certain piece of information. I did define that for you, but you can largely figure out even just from this kind of example input. But let's start from the beginning. It says the name of the function is func, and that is a capital C. In order to write a function, I'm going to use the function, and then I'm going to put curly brackets. And this is where my code goes, and this is where my arguments go. That said, let me demonstrate kind of good practice, even if this is a fairly simplistic piece of code. But if I'm trying to figure out how to write a function, it can sometimes be a little bit tricky. So oftentimes my first step is to kind of erase everything, create some test data. Y, let's just make it will be down here 3, and then Z should be default value of 2. Well, in this example down here, there is a second argument. That second argument needs to go somewhere, and so I say X, Y, and Z in that order, which means my second argument would need to be 2, and so that would end up going to X, not because X is the second argument, because X is the first unset argument, which when I call things, that means it will go to the first argument if Y has, well, it doesn't matter. Y has already been set, but that doesn't affect things because the first argument is X. Cool. So there we are. This is me setting up the code to test it. If I then do X times Y plus Z, hey, it is currently working. That's great. Now I need to start figuring out how to put that into a function. Well, the easy thing is I can just copy and paste that into a function. I could make an out for this. So I could make a function called out, and then I could return that object. I believe in my example, I just put return around this code by itself, which is also fine. There's very little difference. There might be a very, very slight computational difference between these, but it's incredibly small. So very, very similar, whatever helps you think about the data. I do always recommend that you use the return function. Again, not because it's necessary, but because it's just a good strategy. It does help you control. And in those odd cases where it can actually be a little bit challenging to understand what comes out, the return helps you control that really robustly. Remember, one of the big ideas is to isolate your environments. Now, to finish off making this function a function, I got to tell it what its inputs are. We don't want it using the objects on the outside. If it's using objects on the outside, it does get very complicated. You have lots of variables flying around. You just don't want it. It's not good strategy. R is not really built around the assumption you're doing that. And so there's no warnings or anything. It just will pull data from the global environment if they're not set up inside your function. And so my general recommendation is whatever names of objects you're using in your global environment, don't use those same names of objects in your functions. Now, the nice thing is functions don't talk to each other. So if you are using one function or another, they will still go to their parent environment. So I can use a function in my global environment, then use a different function, and those functions can share object names. It does get a little bit more complicated when you have functions calling other functions, which is fairly typical. But that's maybe to get started with. Just avoid it. It's a good move. Scoping is out of scope for this class, largely. All right, so lastly, we just need to finish off that arguments section. In this case, I have given them the right names, but I haven't given them any default values. So to make a default value, you just say equals something. That's the value that it is unless the user specifies something different, either via a named argument or an unnamed argument, in which case it's applied based on order. Okay, the last step of our process for writing functions is to clear your environment. I cleaned up my code a little bit, and then going to run my function and test it, and hey, it is working. So that was a few different steps, but in summary, you write the code using some test objects, you functionalize it, so like basically wrap it in these parts that make it a function, add a return argument, check your inputs, things like that. Maybe experiment with a little bit, but eventually then clear your environment and test it. And then just kind of repeat that until you get it. It is often iterative, especially for more complicated functions. I don't get it right the first try. I have to go through some debugging. It takes effort. Coding isn't, just super simple. It's fun, I think, but it's not simple, which is why I think it's fun. Anyways, let's move forward. Next question. Wrong screen again. Write OE, so odd or even, is going to print a message if the value is odd. This won't necessarily be true based on the way we're doing it. I think I actually took out that error message, so that's why I had that in there. And then I give some tips. So I talk about the mod function or %%. So %% returns the remainder. So if I just had run that, I did see a lot of students who were just like, I don't get it. And I'm like, have you tried running it? And they're like, no. And I was like, try it. Try to understand. Experiment. Be a scientist. Explore. Have some fun. So if I try this again, nope, wrong keyboard. There we go. Nope, still not it. There it is. I'm a little bit blind. My microphone's in the way. So here, if I have 7, the remainder divided by 2 is 1. 8 divided by 2, the remainder is 0 because it divides cleanly. 9, 1 again. Notice a pattern. That's going to continue. This gives us something that we can then test, which is great. All right, so what we want to do is we want to be able to use it like this. Oh, I did leave this in here. So this is where I'm saying that there are errors with a very basic way. The basic path that I took was I basically just did a test. So let's just make an input object called x. Did I say, yeah, I didn't tell you the name of the argument, so let's just name it x. And we'll just make it 1, easy enough. And then, so I said if x is divided by 2, but that's not logic yet. Turns out 1 might work as logic, but let's make it a logical object. So there we are. So 1 divided by 2, if the remainder is 1, which it currently is, then print it is odd. We'll just make it more fun. Ooh, exclamation point, so dramatic. We could then do an else, and we could just say else always print it is even. But the question is that true? Is every number that is not odd even? And the answer I don't think is yes. The answer is definitely no, because even is going to be divisible cleanly by 2, and then odd is going to be cleanly divisible, so it plus 1 is divisible by 2 cleanly. So the opposite of odd is not even wholly. There is another case of neither odd or even, so really any non-integer value. And so the solution becomes that if I had instead done this one actually is better than the function that I put into my code. But that is the idea. In this case, there is nothing to return. I didn't ask for you to return. I just asked for you to print a message. And so as I was talking, I finished up writing that function. We can then just test it real quick. So that is printed. That doesn't print anything. Let's clear our environment. Checking the code. If I run that, it prints off that message. If I run that, it prints off that message. If I run this, my method doesn't print off anything. And so that is a different behavior than if you had come in here and you had done else. So here 2.5, because I'm doing else, which is going to run every time it's not odd, I'm getting is it even? And so it's because it's an immature script. So let's go to the next example. We'll make it more mature, put some more different case examples in it. Gotta remember not to save this file. All right. Next one up is asking us to rewrite OE so that it first checks the inputs class and length. So I'm just going to go copy paste because I'm lazy. Okay. We're going to have it stop if the function is, if the length is wrong. So if x is length of x is greater than, I guess, 1, then stop. But what if the length is 0? Well, that's not maybe the best solution. But if we change it to not equal to 1, then that's actually a pretty decent solution. Sad face. All right. So that works. I generally recommend that you practice this style of organizing your if statements. You know, for a one length code with like a fairly short logical section, is it really necessary? Probably not. But just as you're getting started, I do recommend that you try that. So this next one is saying the input, the is dot numeric of the input is false. So I want it to be maybe numeric. So I will only want this to run if it's not true. So if it's not true, I want it to produce an error message saying it is not numeric. Finally, there's a third warning I'm asking it to do. Make a warning instead of an error. If it's not an integer. Now this is going to be a little bit more challenging, it turns out, but let's start testing the code and trying to figure out how to make it work better. So I'm just going to add some comments in here to give us some clues on what's going on. So check the input for expected properties. Run the logic. All right, so let's test a few things out. We will need an x object to do that, so let's just create one. We'll say that x is 1. Well, if x is 1, we can kind of start going through this. Okay, so that means that this should be false, which means that if I just run it from here, nothing happens, which is good. Had the length been wrong, it should have gone. So I could test that. So let's make x 1 through 2. I want to check that. I do get my message. So that would stop this program. It would exit the function. It would no longer continue. So let's finish let's fix the length of A. Let's make it 1.5. It'll help. So here I'm testing if it is numeric. So it is not numeric. It is numeric. And so this function does not produce a stop message. Had x been something like the letter A, that's not numeric, so that doesn't work. Okay, so that one's working good. This is.integer is going to be a little bit interesting. So is.integer. Well, 1.5, definitely not an integer. No way it's going to be, oh, I did mess up. This happens all the time. This is why we have to do debugging. And then I said to make it a warning because I still wanted it to run the code inside, but I just wanted to produce a warning. Like, is this okay? Like, just more telling the user that this happened, and so allowing them to make the decision on whether or not they should continue like interpreting it. But it doesn't stop the code. That's the difference. Okay, so when I run this, I do get a warning message. If it's not an integer, is this okay? Now let's try to make it an integer. X is 1. Okay, so back to an integer. Or is it? Yeah. So here's the deal. The is.integer checks for the type of data. I guess it potentially checks for the class, but I'm pretty sure it checks for the type. We could check that. Is.integer. It tests if the data is type integer. But what it doesn't do is try to see that, all right, could I make it an integer type? Because just typing a number, by default, it's going to create a numeric object. To make something an actual integer, I'd have to put this capital L next to it. And so now I don't get that warning message, but without the L, I do. And so the solution means that we need to do something else. And there's a lot of different ways that you could do this. I think one of the better ways that I've come up with is to convert it to an integer and then see if it's still equal to the same thing. So even if X is currently not an integer type data, and now it is an integer type data, when we compare them, they will still be both coerced into numeric type, since that's the safer coercion. And so I get true or false if it's not. And so if I make that not equal to X, then that is going to produce an error message, or sorry, a warning message, only when this is unable to happen without changing the value of X. And that's kind of the summary. So there's a lot of different solutions you could have come up with here. This is just one. I like this solution though. Okay, so let's just test that out. So if I make this 1.5, so now when that becomes 1.5, that should get converted into 1. Oh, maybe that didn't go. Let's try 1.5. Okay. So if I print off X, it's 1.5. If I print as.integer of X, it's 1. Which is why this returns true, causing this warning message to be triggered. All right, tricky, right? I know, I'm very tricksy. All right, so at this point, the rest of the logic is the same. There's still nothing to return, and so I believe we've successfully modified it. It is odd. Nope, I forgot I needed to make that OE2. It is odd. It is even. 2.5, it is even. It is not an integer. Is this okay? And then it's not numeric. Length is wrong. So doing good so far. So hopefully that makes sense, but that's the idea. So let's keep elaborating on this. Oh, no, I guess that was the end. There's a couple other things you might want to be able to check. So like this one. I still am producing this message of it is even. So I'd prefer to get some sort of output that is either just empty. So that's where we could do this. So I guess technically that seems to be what I had done when I wrote this warning message, because this didn't output anything except for the warning message. Now, I think often most of you wanted to do some more complex code. You wanted to do like an if-else statement, else-if statement, I should say, where if this was not true, it then tested this one, and then finally it produced a third output. So it is neither, I'm not a horse, neither odd or even. So cool, right? There we go. So That method works out pretty well. It has one condition. It has a not completely exclusive, or sorry, it is an exclusive, but it's not it doesn't check all other possibilities with this second if statement, which means that this third else will occasionally go anytime that neither one of those was true. I'm going to make this more like confirming it is even. All right, let's check it. It is odd. It is even. It is neither odd or even. And then I got this message. It is not integer. Is this okay? So that's the idea. All right, let's put this more into some biology context. Now, I say that you'd be surprised how often just doing some simple math is part of the biology. That said, let's use like an algorithm. In this case, the Hardy-Weinberg. Wingberg? Come on, Nolan. Weinberg. Like I said, all typos are blamed on Kira. She's just very precocious. So in this example, I want you to write a data frame, creating a function that makes a data frame that summarizes P, Q, PP, PQ, QQ, all of these outputs from the Hardy-Weinberg equation. The cool thing is that for the Hardy-Weinberg equation, if you're assuming two alleles, you're assuming that the population is randomly intermating, and you're assuming essentially it's an infinitely sized population. Just that way, you know, you're just working purely within proportions. If you assume all of those things, the distribution of alleles in the absence of any sort of selection pressure is purely based off of the frequency of just one of those alleles. And that's because if I can find the frequency of a one allele in a biallelic system, biallelic being key, that means that the other allele is present at 1 minus that frequency. I can then, assuming random intermating, determine what the different genotype proportions are. So that P squared will give us the proportion that have homozygous P. 2 times P times Q will give us the proportion that are heterozygous. And then Q times Q will give us the proportion that are homozygous Q. This does all equal 1. That turns out to not really play an important role in this other than maybe allowing you to figure out the algebra through a system of equations. That said, in the end, if you think about it, this is essentially just a Punnett square, but a Punnett square across an infinite population size. So then we're just kind of averaging there. All right, so let's do this. I'm going to write a function. It only needs one input. You know, I've been using a lot of X. Let's just use P, because P is what I'm wanting you to use as the input here. So we're calling it HWE. And then its input is going to be P. And we're going to write some code inside of here. Now let's give P a default value, or a value just for experimentation's sake. So while we're writing it, we have something to experiment with. So if P is 2.5, then we should be able to calculate Q by just doing 1 minus P. True. All right, that worked. I tested it. I ran it. It works. Let's calculate homozygous P. So that should be P to the power of 2. Then het should be 2 times P times Q. Enough. And then homo Q will be Q to the power of 2. Cool. Now, if we did that right, these should add up to 1. And we could, I guess, write an if statement. If all of that together does not equal 1, so I could write it like that, or I could write a non-equals. Stop. How did this happen? However, I know mathematically that's not going to happen. There is no, let's see, what happens if I made this a negative value? Still true somehow. All right, clearly that's going to have happened. This became negative 6.25, and then this was 1.625. So yeah, so mathematically this is just not going to change. And then what if this is quite large as well? So does that make it happen? No. All right. So in the end, this ends up not being necessary. I could have like gone through all these examples. I could just reason it out mathematically. I could have left it out altogether, but in the end, I don't actually have to check that. And that's just because of how this math works out. I guess specifically because of that right there. That since Q is always based on 1 minus P, this always will add up to 1. All right, well, now that we've kind of written the math behind all this, all we had to do is assemble the output. So let's just call it out. And then I wanted each of those different values inside a column kind of based on the name of the object. So that should be pretty easy. So data frame. So we'll just call the column PP, column QQ, the column of the homozygous P values. We'll just call that PP. So homo P. The PQ will be het. And QQ will be homo Q. Q. Got it. Finally, should return your data right there. So like I've said before, there is lots of ways you could write these things. We could have put all of this math into just a data frame and return that as one huge line of code. There is probably a very, very slight difference, but honestly, there might not be, at least not a perceptible difference in performance. Also, I generally don't recommend that y'all worry too much about performance at this stage in your career. You get better at it as you practice this skill. The most important thing for most of you is simply getting started and starting to develop the skills of doing things like turning a concept into a function, which can then be easily repeated, doing all of this math based off of a single value. That's fantastic. That's a big skill. All those details like efficiency and optimization, they come with practice and they come with some more training. So let's run this and test it. To test it, we're definitely going to want to clear our environment because we created a lot of objects just now. I think if I were you, I probably would have kind of erased everything and then just tried them after creating a single object, but I know this one's going to work. So here, if I run my function, I test it. P is 75, Q is 25, PP is P squared, PQ, QQ, I could add those up, but they add up to 1. Cool. So next up, remove QQ. So we're going to model a lethal genotype. Ooh. Write a function that recalculates P, assuming all the QQ individuals die. So the input will be the output of HWE. So, for example, here, we're going to take that as our input, and then we are going to remove the QQs and then recalculate things. This will be a little tricky, so we'll have to actually do a little bit of, modeling math. I did kind of tell you you can calculate the total number of P alleles in the remaining population, then the total number of alleles that are not in QQ genotypes because they died. We don't have to worry about the fact that they died here because there are no P alleles in the QQ genotype. That is then going to be returning our new value of P. And then that way we can use it in a next generation as part of a loop, which is the next question. All right. So here I am just giving us an example. So let's just start writing our function with that as our input. Now let's give it a different name. I always recommend using a different name. So we'll call this, I don't know, did I tell you what the name should be? All right, so we'll call it start HW, okay? So this is going to be our test argument. This is what we'll name it. So I'm going to start the function. RMQQ. Cool. And then we're going to make that our input object. So from this, I can extract using the $sign because it is a data frame. I need to calculate the proportion that have P alleles. So there's currently some P, there's currently some Q. I could technically calculate Q times the proportion. So I could subtract from this frequency the proportion that died. That's a little bit more complicated math, but the very easy math is that PP and PQ are the only individuals that should survive. And so if I'm calculating the total number of alleles that are P here, well, this would be times 2, because there's 2 alleles per individual. Then I could do PQ, not times anything, because times 1 is how many alleles they have. And then we'll just call that numerator, just to separate it out, because I really need to. We'll call this denominator. Why do I always do? I can't spell denominator, obviously. And so now this is the total number of alleles that exist in this surviving population. So they both have 2 alleles, so it's just that value. And so then our return, so our quotient, so the new P, I guess, let's just call it that, will be the numerator divided by the denominator. Now, I still didn't spell it right. There it is, denominator. Okay, let's test that out. Okay, so we get this. I can check that against my example, so it looks like that should be right. We just need to remember to use that return function. Again, it turns out, I think, in fact, that case, it would have returned new P, but it can be a little bit tricky. And so my recommendation is to use the return function to manually call return. So let's clear our environment before kind of doing final checks. Clearing, running the function. I could try running this, but I'll get an error message saying that this wasn't created. And I'm like, oh, yep, still got to go make HW input. So we'll just paste that down here for our checking code. We run that. Oh, don't have HWE. We'll have to go rerun our HWE function. This is part of the challenge. It's why I eventually start coding in the a script file, and then I just source that script file every time I save it, which puts all of the functions I want back into my environment. But let's continue with this demonstration. So now I should be able to make this run. Cool, that's still working as we would expect. I then run this here. That's looking good. It returned the right value. I can even nest them together if I want to, still returning the right value. So we're good to move on. That is currently working. So this last one asks you to simulate a situation like a disease outbreak. It wants you to use that remove QQ to simulate a death where each generation, the QQ genotypes die out. So this is like a selection pressure, a very strong selection pressure, because it works 100% of the time on everything that has that QQ genotype. However, it does also model a fully recessive lethal allele. So this is just an allele where, if you have one copy, you're fine. The functional copy typically is what's going on. That functional copy is sufficient. And in this situation, it doesn't even the presence of the bad allele doesn't confer any disadvantage when there's only one copy of the bad allele. But when you have both copies, you completely die. So selection pressure. Cool. Let's go inside. It's going to have 2 inputs, init P. So let's just start it off. What am I going to name it? I don't remember. Oh, I didn't ask you to name it. Oh, I did. I gave you. I was so nice. Let's just do the whole thing. That'll be more fun. We'll see how well I line up because I didn't look at it just now. So you're going to see my whole process here. So I'm going to write a function. So I'm just going to call it, I don't know, like loop RMQQ. Sorry, not very creative here. Init P. So function. Init P max gen I'm not going to give it any default values. I want it to loop through, I guess, a nitp time, a number of generation times, and then it's going to go starting with this initial p-value, but then that will change. Make the output the final p-value, and a plot should be produced. Oh, fun. Good job. Well, let's just get the initial code to work. So a for loop is going to be our easiest way to do something, a process, a certain number of times. I usually use I. Could be really whatever you choose. And then I'm going to do 1 through max gen, and because I'm going to start on generation 1 and go through there. So here are init p. So I guess init p is going to be used to create our current p from init p. But I don't want that to be repeated every time it loops. I just want it to happen the first round, or before the first round of the loop. But since this is a function, it always is going to get run in order. And so I can put it outside the loop. I don't even need to write an if statement. I could though. Okay, so we're going to calculate based on current p. So that will be that HWE function. So let's give init p a default value, or a test value. We'll call it 0.75. Cool. So that means current p will become 0.75. That means HWE will become this. So current HWE. Cool. Then we're going to remove that QQ. And so remove QQ. UP. And when we do that, we're going to then, I guess, add new p to the plot. So we're going to plot new p as a function of the generation. So the generation would be on the x-axis. Time is usually going to be on your x-axis. Your y-axis is going to be the kind of value that's changing typically in response to that. So in this case, the first round, this will plot the new p. Maybe not what I want. But I guess that's more generation 0 is the initial p. So yeah, I think that's right. But the problem is that it means that we'd be skipping that first generation, that time point 0. And so I think eventually we're going to want to add in something else. Additionally, plot will start a new plot every time we run it. And that's a bit of an issue. So there's a few things that we can do. We could write an if statement. So if I is the first time the loop runs, we can actually start a plot. And so we'll have to make it time point 0. So not I, but 0. It'll be init p. So we could do it in an if statement out here, or we could just start it before the function ever runs. Okay, so there's going to be a few problems with that right now. This is just going to be a very small plot. Ironically, still too large for my pain when it was small like that. There we go. So it's just a single dot. That's going to be a problem. Also, our y-axis is very narrow. Our x-axis isn't even close to large enough. And so we're going to probably want to manipulate the limits of this plot. So xlim equals c0 through, well, we need it to be as wide as the number of loops we're going to go through. And then the ylim, well, there's only a certain number of ranges it could take. So 0 through 1 is pretty conservative. That means it's always going to be sufficient to hold all of the data. So if I run that, I have to have a max gen object to do this on. So let's just create a test value for max gen. Let's just say 10 loops to start off with. And there we go. Cool. So at this point, wrong window. So at this point, still the wrong window. Let's continue writing that loop. So here we have our current P. We then plot it, may produce a too narrow of a plot, and then we're going to start looping through everything. So this is going to start off at I of 1. We don't really need to use I. We could, but there's a couple of different ways to work around that. I'm then going to get the current HWE from the current P. We're then going to create a new P. I can then add a point using the points function to our plot. And so we could do that at I and new P. Oh, we need a test value for I. Let's just make it down here. All right, so we can see that that's changed after 1 point. That should continue. I can manually then progress to the next one. And what I would find is that because of how I've written this, that doesn't currently work. It hasn't changed any. Well, and the reason why is I made it new P instead of overwriting the old version of current P. And so that's really going to be the strategy, is to make this recursive where the previous value affects the next value. And then it just kind of keeps going. Now, since I replaced new P, that means I'm going to need to replace it here too. But at this point, now that I've done this, I run this here, I run this here, I run this. And if I remember to iterate this process correctly, it's now going up again. So let's change the plot back to the starting point, change our current P back to the starting value, and then we can run that loop. And there we go. You can see the dots appearing above my head. In other words, this is now starting to work correctly. There's a lot of different ways that you could write this. This was just more trying to simulate like kind of how we muddle through this process. Now there's a few considerations that we should probably be mentioning because this is an educational video. Instead of relying on this process where we generate a value and we overwrite the value, we could instead have just been adding to an object and then like plotting the most recent value. And then for the next iteration, we could be pulling from that. So that would be like building. It would allow you to first have even created an object to store all the data. So if you're doing this for 10 million values, you'd probably want to set aside a section of memory to hold those 10 million values before starting the loop. That's a much more quick way of doing that type of analysis. I'll give an example of that later on. So let's just stop there. So to test this out, we need to make it a function. So right now we're good. We don't actually need to return anything from this. Oh, I did actually. So I said the final P value, and then the plot should also be returned. So I need to return the final P value after the loop is completed. Okay. So let's test that out. I'm going to clear my environment here. And let's say the initial value is 0.2, and then the maximum generation is 10, I guess. Oh, couldn't find the function HWE. Yeah, gotta go rerun all those functions. All right, this is why it's really helpful to put it into a source file, because every time you source that file, they all get run. All right. Now that we got our functions loaded, that does work. We're able to then, and it finally reproduces the output value. We could check this down here. Oh, I called the function disruption before. All right, let's go do that. Cool. 91. 99. Yeah, and so there you go. They're doing some ecological modeling. All right, so looking at this version, I can see that I want to change it so that it is able to just work. So we'll call this disruption again. I need to write a function. Come down here. I'm going to indent everything. Make my screen a little bit bigger. So this if statement, when if is 1, well, we don't want to be overwriting p each time. So we're going to make p based on the init, or sorry, it was called init val. There we go. And then max generations, max gen, that's what we call it, right? Max gen, yeah, with a capital G. And so max gen should be controlling this for loop. So I would want that to be changing how many times it runs based on that value. And then anytime I is 1, I am setting the initial p value. I'm then creating a plot, but that plot should go to certain extents based on the input values. Y-lim of 0 to 1, that's fine. Pitch is the type of point. So if you change that, it changes the point. Here, I start off by plotting a single value. X equals 0, that's fine. Time starting at generation 0 is fine, but I would want Y to be starting at the initial value, or we could just change that to P, actually, since initial value has already been used to create P at this point. They are equivalent. There was no benefit to using one or the other. I then create HW out from HWE of P, and then I overwrite that version of P using the RMQQ, and I make a points from it, and I made a rainbow. I added, rainbow is a function that generates a number of values equal to the input, equal in length to the input value. And so right now, it's just hard-coded at 20, but I'd probably want that to be set to max gen, so that way it didn't produce an error. I guess I could just really overshoot it, but then I wouldn't get the full rainbow effect scaled across however many generations I did use. All right, so finally, that's the end of the for loop. I then just need to return the correct value, and should be good. So I said init p, and it's because I called it init value. So init p. Init p. Cool. Let's clear our environment. Actually, we're going to use that fancy code from down here to remove everything but our disruption function, or everything but those previous functions, so I don't have to go back and rerun all of those. Now let's try it out. And hey, look at that. It is now in fact working. And I get a cool little rainbow effect, which is fun. So I can simulate 100 populations. I could get a really, really low initial value, and I can see that it's basically unchanged. And that's because that selection pressure is quite large, with a massive change just between that first and the second generation. Cool. Well, I'm going to cut this video off here, and then I'll make a second video for the polls. So if you want to go through these, I think I've already kind of written some answers down in here, but explore the recursive loop and determine the point where death rate begins to cause the population to decline. So that recursive loop up here is... There it is. Initial population 1,000, growth 1.5, death rate 2.0, time, and then running the loop, and then plotting those results. Okay, so we can see the population growing. If I start to increase this death rate, we can see that that went up. If I make this 3, this value actually decreased. So this is actually just becoming a little bit more linear. So we're doing less exponential growth. That's why it's appearing to go up, but the actual values are decreasing. And that's just because of the aspect ratio, really. If I then get it to 3.3, I can't remember if 3.3 does it or if it's just really, really horizontal at that point. Yeah, 3.3 just barely grows. So we're really, really slowly growing. And then anything above 3.3, just because of the relationship here, quickly dies out. So down here, we suddenly start to die off. If we make this even higher, it gets lower and lower. And if we increase the time on this, eventually it just gets to 0. And that's really just any time that you're increasing this death rate. I think above 3.4. It still doesn't quite reach to 0, but anything above 3.3 repeating is going to start causing the population to die off. Now, obviously, that's quite a bit of death. That means that there's a large amount of the population that is failing to reach a reproductive age. But yeah, so that's kind of what I meant when I said explore this, play with the numbers, come to understand this code in here. And so if I try to do that, if I go into this, I can see that there is a loop of 1 through times, and when I increase this, it just ran the loop more times. Here it's creating a object called cur population whenever I equals 1. And so the first round of the loop, it's going to set all of this up. And then subsequent rounds of the loop are going to be based upon the recursive effects of this process. So this process is have the current population die back some. So take the current population, subtract out a proportion that have died. So that's why I call this a proportional death rate. And then I'm just rounding it just to kind of make the numbers a little bit more realistic. In the end, I mean, we're not worried about sex dynamics in this. We're assuming intermating and just all sorts of things are being assumed in the background. This is a very poor model. It's just very simple. I say if the population is less than 0, then make the current population 0 because a negative population won't exist. It's kind of like that read depth thing. This is a discrete value because, yeah, individuals are discrete if I'm actually trying to model the size of the population as opposed to a infinite size population modeled in that Hardy-Weinberg equation. Finally, I then grow, again rounding, just because just trying to stick with discrete values. And then here's where I'm kind of doing what I was talking about earlier and actually adding to my output to an object that will just grow larger and larger with each round of the loop. And so this just is a way to save my output. It's not really the most optimal way. I think the most optimal way would be to first create an object that is the right size. So usually I'll use a data frame for that. So I'll create a data frame with a column of time. So I'll just put df1 data.frame, and I'll say time equals 1 through time. And then I'll just have a value of pop or something like that. And I'll just start with some NA values. And then each round of the loop, instead of adding it together like this, I would extract that population and then place the current population into the right position. So if I do this, I come out with a data frame that works real well. And so at that point, I would no longer need to do this, although I would probably want to add in my 0 and my starting population size, which my current method didn't really facilitate. So I could change that. I could make that 0. I could make df1 $pop. And then instead of adding in at the ith, I would add in at the i+1. And so at that, because of that modification, this is time of 0, we had that initial population, but then I was adding in new values at the generation plus 1. So at the second row is the end of the first generation. And like, you know, I've practiced this enough that I could just kind of just do it. But that is something that takes practice, like just kind of finding the right position and like tracking in your head the effects of a loop is always a little bit challenging, but definitely doable. So that's the idea. Cool. In this next example, I think it's fun. It's a little bit much, and so I'm not going to go through it in this video. If you do want to talk about it, come to tutorials. We'll go through it. It's a cool process. It builds a 3-dimensional array with an I, J, and K. It is a horribly inefficient method of doing things, and that's actually just kind of getting at the nature of for loops in R. They are, in fact, very slow. If I really want to repeat a process, especially once I've kind of figured out, all right, I've worked out the math, maybe I even know what the output should be, but it just takes forever to do. This is legitimately what I end up doing quite a bit. I will have written a for loop that works super, super slowly, but I can figure out what looks right. Then I muddle my way through the apply series of functions. I actually had to do a little bit of research to figure out this reduce function. I never use reduce. And so the apply functions are much faster. And obviously I did all of that code in essentially 3 lines of code here. So they're also much like simpler in that way, simpler to code. But in the end, it produces a neat little heat map with some unique clustering. So have fun with that if you're interested, but I'm going to call this the end of the video. So thank you and bye.